Bom, boa tarde a todos. Daremos início a mais uma palestra do 10º Workshop de Engenharia de Biosistemas. A gente pede que vocês se inscrevam no nosso canal e cliquem no sininho para receber as notificações ao início de cada palestra que será transmitida online. Fiquem à vontade para colocar as suas perguntas nos comentários do YouTube durante toda a apresentação. Convidamos o professor Dr. Sudhir Singh para ministrar a palestra Avaliação da erosão do solo na bacia hidrográfica do Himalaia, segundo modelos climáticos recentes. O doutor trabalha no Banerjee Centro de Estudos Atmosféricos e Oceânicos da Universidade de Allahabad. Possui interesse de pesquisa em sensoriamento remoto, geoinformática, biogeografia e qualidade da água, além de mudanças climáticas, modelagem ambiental e modelagem hidrológica. Atualmente trabalha no projeto SERB, DST, lidando com o impacto de mudança de uso e cobertura da terra no fluxo ambiental. E também faz parte da equipe BRICS, para liderar o impacto da mudança climática em bacias hidrográficas selecionadas da Índia, África do Sul e Brasil. Now I will hand it over to you, Sudhir. You may start your presentation.
Yeah, thank you, Anna, for my nice introduction in Brazilian language. Actually, some of words I have picked, so thank you very much. So I start my presentation. I think it is now in the full screen mode, presentation mode. So first of all, I will tell you that the place where I am basically working, and the place is known for the big gathering, big holy gathering. Actually, there are two river system. One is our Ganges, and just like your in Brazil, you have a major river system. So similarly, in India, we have a one river is Ganges, and second is Yamuna river, and there is a confluence. And every like in 12 years, we have a big holy gathering that we called is Kumbh. Okay, so in next year we are going to suppose have more than we can say that more than billions of people are going to take a holy dip. So that is our the just introduction about the place where I am basically working. That is called in basically nowadays you will find that that is called Allahabad, and that is a university. And so my topic of today's talk is assessment of soil erosion assessment of soil erosion from the Himalayan river basin under the recent climate models. Okay, so that is the topic of the talk is assessment of soil erosion from the Himalayan river basin under the recent climate models like CBIP 6. So I hope you all are aware with the kind of the degradation basically we are basically facing in an environment. The most common degradation is the soil degradation. So soil degradation that can be like from the natural process. When we have a glacier, this we can see that there is a natural process and there is an anthropogenic process through which we can remove the top layer of the soil. So the top layer of the soil, why it is important, how we are going to control the soil erosion, and what will be the forecast, like if the temperature is going to rise, if the precipitation is going to increase or decrease, then what will be the kind of problems we are going to face in terms of loss of topsoil. Topsoil is a very fertile soil which helps to grow the crops, correct, and which also controls in balancing the carbon dioxide, like the land is also one of the best place where carbon dioxide can be sequestrated. If we are going to disturb the soil, then we will find that the CO2 is going to release in the atmosphere, and that is going to change our climate, correct. So there are many ways actually we are going to increase the soil erosion, like livestock grazing. If we have unbalanced livestock grazing, then you will find that soil is going to be erode. Similarly, we are using this mechanical these heavy machines for farming. So that is also going to increase. Similarly, there are many other activities, like if we are going to do the urbanization, we are going to cut the trees, then we are going to basically make the soil uh, prone for the detachment through either through the forcing like wind, or through the water, or through the glacier. There are other forces are also. So that is the thing which we are going to discuss, the types of soil erosion. Everyone know there are different types of soil erosion. and we are in all with our part of the nation, like in our country we have different kinds of erosion, like seat erosion, then rill erosion, gully erosion, and wind erosion, mass erosion, and tunnel erosion. Like the first phase of the erosion is the rill erosion, through the water, the concentrated water. When it falls on the soil, it runs, like it form a small channels. These channels are called the rills. Okay, so rill erosion is very common in the plain areas. Similarly, if the rill erosion is going to be intensified, then whole sheet is going to be eroded. And if similarly, like other the way, if sheet erosion is deep, then we are going to form the gully erosion. And wind erosion, through the basically wind or dust is going to continuously hit, then you will find these kind of landforms are very common in our, like in our part like in central India and rest of the world. Similarly, tunnel erosion. So here these types of soil erosion is very. This is a very brief actually way to understand what kind of soil erosion I am going to target. Correct. So I have one specific region which I have targeted. Why we have I have targeted this region? Because the Himalaya, like in the Andes, Himalaya, Aral. There are so many mountainous regions all over the world, and these mountainous regions have different kind of topography, different kind of slopes, and different kind of basically energy balance. Correct. So in this region, like in Himalayan region or Himalaya, we are continuously facing the impact of climate change. In Himalaya, we have Eastern Himalaya and Western Himalaya. Similarly, we also have a Central Himalaya. So Eastern Himalaya, Western Himalaya, there is a difference in the melting melting rate. There are lots of peoples have worked on these parts of the Himalaya, and they find that there is a differential melting or differential heating they have observed over the Himalaya in different parts of the Himalayan range. So I have targeted one river basin as a case study. The river originated from the near to Mansarovar Lake, which is near to China border, and it runs through China to Nepal, and then it comes to our part in India, and later on it merges with the longest river of India, that is Ganges. In Ganges, it is going to merge. Here you will find that in this site where a person is standing, and previously he was growing the paddy and wheat in this land, but due to heavy this flow, large flow or intensive rainfall, the whole land mass is going to be detached or is going to be eroded. So you will find that the soil moisture is continuously, you will see the from the lower to the top you will find that there is a dry, and in the bottom you will find that is a wet. And when top is also going to be wetted, it is going to sink. The whole landforms or whole landforms is going to be sink, and this land, the fertile agricultural land or arable agricultural land is going to be detached, and there is a lot of the agricultural losses and yield loss and all. So we have taken this as a case study. This is the floodplain of the river. Okay, in different parts, like there is one district, we called it district, that is an administrative unit. So here you will find that a person, one of my scholar and I was standing, and we are going to see. You will find that there is a small rills are formed, and then these small rills are going to combine, and then there is a seed kind of erosion is observed. Okay, this whole the the biggest problem with this river is this, like the river is continuously meandering. The river is continuously changing its shifting its pattern, and this shifting its pattern is basically regulated by the rainfall, and it also regulated by the discharge or stream flow which river is carrying. So these kind of problems, I hope you also find in the Brazil or other part of the world. So here you see there is a continuous like seed form of erosion. Here if you see, in one person is standing below, and then you will see, you can count that how many events has occurred, and those events has eroded the soil actually. You can see actually. So similarly on the left and right side, there is a lots of erosion. We have estimated these kind of things. This one side you will on the right side you will find that there is a agricultural field, and over the period of time, this agricultural field is also going to be banished if the river is going to change its course due to anthropogenic activity, climate change, global warming, or simply we can say that erratic behavior of rainfall. Correct? Or there is a erratic behavior in the discharge or stream flow. So these kind of the things basically we have first we have visited the field, then we have conceptualized the idea that okay, this kind of problems we are facing, how we are going to model these kind of problem, and how we are going to forecast the the things, or predict, we are going to predict that how much sediment we are receiving over the period of time. Fine. So why is soil erosion such a big problem? Soil erosion is a global problem, as I had discussed. It also aggravates the climate change. It is going to disturb the CO2 cycle, balance cycle. CO2 basically this as a sink and source kind of cyclic pattern. It is going to disturb process of top layer of soil being worn away by or transported by natural forces or human activities. And natural processes is like processes are like water, ice, snow, air, plants, and animals. Okay, so through this kind of naturally, basically, and humans, when human dimension is going to be involved, then you will find that the speed or rate of change of this process is increasing. Correct. So this is the basically the thing where we can think of that how we are going to control this the removal of top layer of soil by minimizing the human footprint. Correct? Footprint. How we are going to minimize the human footprints. So soil erosion can have many negative effects like reduced soil fertility, lower crop yield, flooding, climate change, economic losses. So this soil is eroding more quickly than it is being formed. So because it takes like hundreds of years or thousands of years to become a soil particle. So if the top layer is going to be removed, then you will find that the sustaining property of soil as a crop is going to be reduced, and how we are going to feed the 9 billion people like around in mid century. Correct. So if the population is continuously rising in different parts of the world, like mostly the population rise is observed in the Southeast Asian region. If that soil layer is going, top soil layer is going to be removed, then how we are going to feed the 9 billion population? Right? These are the questions we have to understand. So these are the problems actually we have to understand. So what are the models actually? How we are going to model this soil erosion? So there are different types of approaches actually. There are some approaches which are empirical approaches, some are process based approaches. So empirical and process based approaches, both approaches are, as per my understanding, both approaches are good. And depending upon the type of data we have, depending upon the accuracy we are going to predict or we are going to estimate. Correct. If we are going to estimate, so depending upon the our input data, depending upon our resources, depending upon our requirement, we are going to choose different kinds of models. Correct. So there are the main basic equation was developed as a universal soil loss equation, Wishman and Smith 1978. They have just for a plot scale actually. They performed this study for a plot scale. Later on, people have conceptualized this idea into different process based models like chemical runoff and erosion from agriculture management, Krim's model, Kinsley et al., agricultural non-point source pollution model. Then they have revised the universal soil loss equation was revised as a revised universal soil loss equation. This equation is very common actually nowadays. Loosely, then that was a further modified as a modified universal soil loss equation, and later empirical. These are the empirical models. There are so many other models like for different parts of the world, like in Scandinavian countries or in Europe, people are using erosion potential model or Persera model. Okay, so Persera model, they are using the Persera models, and here you will find that European soil erosion model, Eurosem. Then they have a Griffith University erosion template models, Limburg soil erosion models, the very common water erosion prediction project actually. That is also helps in modeling the or understanding the soil loss. These are the basically physical process based models. Here you need lot of data actually. Correct. So we will discuss what kind of data. So I have uh, performed case studies. Correct. So what are the case studies? The region I have already discussed, that what region I have taken. The Himalayan region I have taken. So Himalayan region. What was the region for selecting the Himalayan region? Himalayan river catchment acts as a water tower, because the North India, majority of the North Indian region states, we are receiving the water through glacial belt. Correct. So that's why we are called it as a tower to the downstream region, and feeds the large population of the Indo-Gangetic plain. So Indo-Gangetic plain, we have a big Indo-Gangetic plain, thousands of square kilometers, where we have a different kind of agricultural activity, and majority of the people residing in this Indo-Gangetic plain. And the water is the Himalayan catchments basically, they provide the water. The Himalayan region is vulnerable to climate change, which I have already we have discussed that, which is triggering extreme hydrological events, and this region has witnessed many extreme hydrological events in the recent past. There are lots of hydrological events has been occurred in the past. Uh, I hope maybe you people somehow in the newspaper, maybe you have understood that there was a very tragic actually event happened in the past, like in 2013 and 2021, that Kedarnath flood and Chaboli disaster. There are lots of things were there involved. Basically, we can say that there was a cloud burst, there was a glacial lake outburst, and flash flood. So these three processes combined makes a multi-hazard kind of things. And this Kedarnath and Chamoli, Kedarnath is a very basically, we have a holy place in the Himalayan region, Kedarnath. So that if you see the visuals of those Kedarnath floods or Chamoli disaster, you can analyze that how disaster happened within a seconds. Like there is a cloud burst and immediately there is a flash flood, because there is a steep slope, so water rushes very fast actually, and lots of sands, lots of soil is coming along with the flow of water. So the hydrological characteristics of the Himalayan catchments are driven by India's summer monsoon. Just like in India, we have two kind of monsoon system. One is we call it the southwest monsoon system, and another is called northeastern monsoon. So southwest monsoon, majority of the India, approximately 90%, we can say that 90% of the India is covered by the southwest monsoon rainfall, and 10% is covered by the northeast monsoon. In general, basically, simply I say this statement as a, like, northeast monsoonal rain comes towards the Tamil Nadu region, in the southern part of the India, and southwest covers whole region. So these kind of things basically we need to understand. The Himalayan region receives high rainfall events throughout the monsoon period. Approximately in the Himalayas we receive around more than 2000 mm rainfall. Okay, annual average rainfall more than 2000. And these events generates flash floods in the upstream river catchment during this summer snow melt from the Himalayas remains the prime source of water for the. So as I told you that, like, the Himalayan region is very much prone to this kind of disasters, and if these disasters happened in the Himalayan region, so you will find that these are going to remove the top soil layer. Correct. So which will which will affect our uh, yield, which will affect our economy, which will affect our our social structures, which will affect our, like, migration of the people from that region to other parts of the country. That also affects the socio-cultural, we can say, socio-cultural activities. So disaster not only affects in terms of capital or environment, it also affects the people's, we can say, culture actually. It also affects the people's culture. And in India, basically, we have a different kind of social structure. So the person who resides in the bottom of the social structure, you will find that that person is going to be severely affected by this kind of floods or this kind of disaster like. So this region, actually I have selected this region as a case study. So you can see that the yellow boundary, yellow is the boundary which shows the river basin boundary, correct? So this whole boundary, this whole yellow boundary, consider the watershed area which comes under uh, under the, we can say that in the China, Nepal, and majority in the India, correct? So if you see the right hand side, you will find that there is a white color in the top, then there is a red or brownish color, then you will find in the bottom there is a greenish kind of thing. So white is just like snow, majority of the snow or glacier, there are glaciers. So the area, basically this area uh, has a altitude from 36 or an average 36 meter to 7,700, correct, 7,707 meter approximately, with reference to mean sea level. So this is the height actually. So you can understand that how steep slope may be, correct? Very steep slope is there. So, and we have taken the data. We can consider this for this kind of study. We can consider the data like first is the LULC, then you need the dam, then you can take the population density. We have taken the population density, so world population density from this CDEC. Then you can go for the meteorological variables, like we have taken the observed meteorological variables from India Meteorological Department. We have a very good meteorological department, and that is India Meteorological Department, that India Meteorological Department has more than 100 years old data records. So mean is, and then later on we have taken the CB6 models mean data, mean is sample for rainfall and temperature. So these things like climate model downscaling, I hope you people may know that when we are taking the CBIP6 CBIP6 model data, so these are the high resolution data. We need to basically downscale these products up to our basic scale, correct? So for downscaling, we have considering the GCM downscaling through statistical downscaling model version, this SDSM. And in the SDSM, we have a predictor and predicted, and predictors, we have taken 16 predictor for predicting the variables, so large scale climate variables. So dynamic downscaling and statistical downscaling. I have performed the statistical downscaling, so I have not gone through the dynamical downscaling, and I have not run the any regional climate model like RCM. I have not run. So these are the basically. So here I am showing the output of my the model output, actually CBIP6 model output. So we have considered both the scenario like RCP's representative consultation pathway scenario and SSP recent AR6 report and AR5 report, assessment IPCC assessment report 5 and assessment report 6. By considering assessment report 5, why I have considered the assessment report 5 and why as 6, I want to see that what is the basically difference between both the reports. So if you see that there both the reports shows that there is an increase in the mean temperature, correct? In the mean temperature there will be an increase, and more increase was observed, like if you see, the more increase was observed in the representative consultation pathway as compared to the shared socioeconomic pathways, because in shared socioeconomic pathways the scientists have also considered the technological advancement. So that's why you will observe that if RCP 4.5 and RCP 8.5, if we are considering, then RCP 4.5 shows that there is a increase of around 1.5 degrees centigrade, and RCP 8.5 shows that there will be a increase in the around 2.5 degrees centigrade in the basin. Actually, I am showing these assessment for that basin at a basin scale. Similarly, SSP 245 and SSP 585. Baseline scenario or moderate scenario. For baseline scenario, it was around like increment was around 0.6 degree centigrade, and for SSPs 585, it is around 1.25 degree centigrade increment. So if you see both the diagram, then you can analyze that there is a break, like in break, because up to 2014, CBIP6 data, it is called historical, and after that it is called predicted, like projected to 2050. Similarly here, after 2006 it is called projected, and before that it is called historical. So if you see on the right hand panel, actually uh, I cannot, yeah, here you can see, that there is a sharp increase, correct? So that is sharp increase, but here you will find that there is not a sharp increase. So this kind of this is much better actually picture, because it is showing 1.25 degree centigrade increase as compared to 2.5, 1.5 here in SSP 585, as compared to 2.5 in RCP 8.5, correct? So that is the thing. But overall, if you can see that there is a increasing trend of temperature, that is a sign of worry for us. We have to see that there is an increase in the temperature, whether we are considering the CBF6 scenario or whether we are considering the CBF5 scenario. So I hope similar kind of work, if you can do in your region, you may find that uh, there may be a probability that the temperature is increasing in your region also. Probability, it is not 100% sure, but there may be a probability that the temperature may be increasing because of the greenhouse gases we are emitting in the atmosphere. So here the projected change in the rainfall. So you will find that there is a projected change in the rainfall is observed, like if you are considering RCP 4.5, there is a increase of around 58.73 mm annual, or if we are considering RCP 8.5, then there is a 161.86 mm, correct? If we are going to same, we are going to analyze for this, for same period we are going to analyze by considering SSP 245 and SSP 8585. Then we go for, well, then we see that there is a very slight increase in SSP 245, because there is a no warming, very low warming actually was observed in baseline scenario, so that there is a chance of less increment in the rainfall. But 585, there is a huge increment, and that huge increment, if you read the IPCC report, that is also showing that there may be a increase, there is an increase in the rainfall. Why there is an increase in the rainfall? Because of the this more vaporization and more condensation process. Because of the high temperature, there is a more evaporation from the ocean, and land you will find more rainfall. But that is we considered at the outlet of the basin, where we have this is for the outlet of the basin. Here you see that projected average monthly stream flow. If we are considering the average monthly stream flow, then for same region you will find that CB5 and CB6, correct? So here there are four, that is one sedent error bar graph, one average monthly stream flow RCP 4.45, this blue star kind of lines you will see. Then sedent error bar for RCP 8.5 red, and then average monthly RCPs and average monthly stream flow observed. This black star line, dotted star line, so observed. And here you see that for RCPs, these RC, when we consider the RCPs as an input, then our model, the the projected, when we are going to project actually, then we find that there is a a problem actually. Problem in terms of what? Problem in terms of that models are under predicting. Correct. When we are considering this CBIP6 scenario, then we find that their model is over predicting. Correct. So this is the uncertainties where we have to understand that how we are going to minimize this uncertainty. And if the flow is more or if the flow is less, what is going to happen? If the flow is more or if the flow is less, flow is more, then you will find that there is a more chance of lateral erosion, more chance of erosion, more area is getting flooded, or more soil loss is more topsoil is going to be removed. So this kind of FDCs we have developed like for different models. Actually, the different models we have considered like can ESM, CNRM, CSIRO, GFDL, XS, IPSL, MRI, ESM, different scenarios we have considered. So we find that there is a, if you see here, what it is telling, that it is telling what is the return period of. So return period, if you see 2.5 years, so okay, 2.5 years means high flow. The flow around 2.8 into 10 to power 4 magnitude. That is high flow is having this return period, approximately 1 year return period. If you see this, so return period is going to be increased. High flow and low flows return period is different. By considering this figure, you will find that there is a high flow and low flow return period is going to be different. Here the return flow, if RCP 4.5 and if you see RCP 4.5, then you will find that there is a return flow less than 2.5. Okay, in this case. So return period of flood events of different magnitude under moderate and high emission scenarios. Magnitude of 5-year return period flows were higher in RCP 8.5. And FDC is showed. Why basically we are showing this FDC flow discharge curve? These flow discharge curves helps us to design our dams, to design our reservoirs, to renovate our reservoirs, to renovate our dams. Actually, this will help you how to how basically this will help us to 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 perform the renovation activities or development of new dams and reservoirs. Overall results of FDCs for both the CB5 model depicted that large floods of short duration would be more frequent. Large floods. Nowadays, you will find that the extreme events are very common. Extreme events like either drought or flood. So in a very short period of time, you will find that heavy rainfall in a very short period of time, like, or maybe there is a drought. So these kind of activities are increasing uh, day by day. Actually. So the future climate projections of average temperature of basin showed an increment, as we already discussed, 3.5 and 2.5, 3.5 and 3. And the future change in the rainfall pattern, this is also discussed. We have, and FTCs we discussed. So here this was the basically that was the we have developed the simply we can say that was developed for the discharge. Now we are going to estimate the soil erosion. Correct. So soil erosion, basically this soil erosion is the loss of, we already discussed that loss of topsoil is a global environmental challenge. Correct. Rivers originated in Himalayan and Tibetan plateau supply most of the 25% sediment load. The lower part of Himalayan subbasin are now facing a soil loss problem. The Shivalik formation, lower Himalaya, which is the source of Ganges, has a weak geological combination and thus susceptible to. Here we observe that this is not the Himalaya is not made up of granite kind of things. Okay, so that's why limestone or sandstone. So that is very fragile. Therefore, it is vital to understand soil erosion. The major goal of study we already in this work basically I have select the objective of the work was that what kind of dams actually helps for better estimates of soil loss. So dam selection was the first objective. So here you can see that there are different inputs and different kinds of models are there. We have used the dam, soil, LULC and meteorological variables, and that from dam, soil, LULC, meteorological variable, we have developed the rainfall erosivity factor, K soil loss, K factor means soil erodibility factor, LS means slope length factor, C crop management factor, P practice factor. So these factors we can develop from with the help of these dam, soil, LULC, and meteorological variables. Then we have simultaneously. I have also used the Archido for delineation of water sets, watershed delineation. Then you can go for the water sets and drainage network. You identify the drainage network depending upon the method which you have used, like installer method. We have used the installer method for data network. Then we computed the morphometric and perform the morphometric analysis. We have identified the shape of the basin, then the different factors like form factor, bifurcation ratio, how the river is furcated, and the stream order, stream length, these kind of things we computed through morphometric analysis. Then, based upon compound factor, we have prioritized the basin by applying the multi-criteria evaluation process. And in the right hand side, you will find that there is a Rosetta model, Hydras-Bundy model that that was used to develop the water retention curve, actually, water holding capacity, water retention curve. And in the QGIS, through QGIS we perform the hypsometric analysis. Through hypsometric analysis, we have identified that whether basin is the basin is under the young stage, old stage, or mature stage. Correct. So geomorphic stages of the basin. And later we have validated the prioritized map, cell grid based. So this was the LULC map of the area we have considered from this map was used. This map was used This map was basically generated by the bodies. So body sensor we have downloaded this, and somehow we modify it. Modified. Then, as I told you, morphometric parameters, there are a number of morphometric parameters, but we have considered these morphometric parameters to know the morphology of the river, actually. So stream order, hierarchical methods, we have used hierarchical ranking, stream length, then stream length ratio, then bifurcation ratio, then drainage density, then stream frequency, elongation ratio, circulatory ratio, form factor, shape factor, length of overland flow, basin length, and compactness factor. So they have different factors, and there are so many factors, but we have considered these factors for prioritization of our basin. For more detail, you can consider the references, and these are the important references. Some factor tells us the density of the drainage. Some factor tells us the frequency of the streams. Some will tell you the whether the basin is your elongated or circular. Some factor tells us the shape of the basin. So that is the thing. And these are the basically some we can say that there is some plots which is showing that how stream length ratio is at the sub basin. Total we have identified the 30 sub basin based upon the order of the stream. We have 30 sub basins in our study sites. Then bifurcation ratio versus sub basin, then sub basin versus drainage density, and sub basin versus length of overland flow and stream frequency. So these graphs shows that the sub-basin number 12, like stream length ratio and sub-basin, you will find that 12, 13 sub-basin has high stream length ratio, and similarly 24. Bifurcation is very high in at the 13 sub-basin. So means through this you can analyze that what is the basically characteristics of the sub-basin. For the Ghagra River Basin, total fifth order of the stream was generated, and sub-basin 25 has the highest RL. RL you can see here. RL means the short form stream length ratio. So RL is stream length ratio. 25 has the highest stream length ratio. Sub-basin 13 and 17 have higher bifurcation ratio, low drainage density. So where the drainage density is low, so what is going to happen if drainage density is low? The water is remains in that area. If drainage density is very high, then all the water is going to be drained out. Correct. So overland flow shows the lower value in the upper tracks, and while lower parts have higher value. Means in the upper part lower movement, and in the lower part, you will find very high values. Some basins that are occupied by the highest value of stream texture and impermeable lithology in the basin generally produces faster runoff. If SF value is high, then you will find that the soil is the layer is impermeable, and you will find faster runoff. And that faster runoff, if the velocity of water is very high, then you will find where there is a soil, it is going to erode. Correct. So these kind of things are there. Subbasin wise forms we have already told you, and similarly other factors like elongated 0.78 is there. So basin is elongated in shape, not a circular. Elongated means there is a line of con- uh, line of concert. There is a line of concentration. So how the water is going to drain? If there is a rainfall is there in the top, then how much time it is going to take to drain out from the outlet of the basin? Okay, if the basin is circular, then there is a very short period of time, then you have a very limited time to protect the things. But if there is a basin is elongated, and then you have a lot of time, you can make the channels and channelize the water. So these kind of structures you can draw. Elongation ratio is this one, and which tells us the variability of the climate and geological setup. RE is the highly elongated shapes, circular. Downstream subbasin have lower RC and upper median CC. So these kind of factors we have developed through the this R factor, rainfall erosivity factor. We have different regression models for different regions actually. So we have considered the regression equation, and through regression equation we have developed the annual rainfall factor or rainfall erosivity factor. Correct. So some region receives very high rainfall, some region receives very low rainfall, and similarly K factor tells us the erodibility. The K factor derived based upon this texture, soil property. Similarly C factor, similarly P factor. Correct. And these are the basically LS factor. We simply say that is slope length factor based upon freely available depth data. SRTM 30 meter, loss 30 meter, and merit, and then SRTM 90 meter. Correct. So you will see that the merit 90 meter showing that LS the this LS factor, topographic factor, is showing very low value actually. But when we validated this LS factor by the one European scientist, Pagnos, he has developed this LS factor. He has suggested us that this is not a correct LS factor. You can go for like LS factor SRTM 30 meters is somehow good. So we have validated this with their products also. So SRTM 30 meter, when we are considering the SRTM 30 meter dam, correct. So we are considering the SRTM 30 meter dam, then we have estimated the soil erosion rate, ton per hectare per year from different parts. And when considering the loss, we have different unit. When we are considering the merit 90 meter, that is, and we are considering the SRTM 90 meter. So here there is a table which shows that SRTM 30 meter, loss 30 meter, merit 90 meter, and SRTM 90 meter. Then there is a erosion rate maximum 125 tons, 107 tons. Merit it is showing only 67 tons, and SRTM 90 shows 66 tons. Now we have the observed actually amount, and then we computed the difference. Okay, erosion amount, we have erosion amount. How we have calculated erosion amount? We have calculated the erosion amount by multiplying the pixel value. Okay, this pixel value. Then we computed this erosion amount, and then observed erosion amount we have. Then we found that there is a difference. So minimum difference was observed in case of SRTM 30 meter. It means the SRTM 30 meter dam is suitable for the Himalayan region to Himalayan region Himalayan region for better accuracy. Whereas a Merit 90 meter and SRTM 90 meter is somehow showing lower accuracy or very poor accuracy. Correct. So that's why we are considering SRTM 30 meter. So first was that we have used the CBIP6 models for understanding the hydrological characteristics of the basin. In the second study, we have selected the best dam, correct, best freely available dams for estimating the LS, slope length factor or topographic factor. Later on, we are going to use both the hydrological characteristics of the basin and hydrometeorological characteristics of the basin and SRTM 30 meter. Correct. So this was the overall object conclusion that SRTM 30 meter was more close to the observed. So now we have also developed the water holding capacity curve actually. So here you can see that water holding capacity, the the soil which hold more water is the highest value of field capacity. You will see the clay loam, and how clay loam is VD, the first curve, this one. I hope maybe color are not too visible this, but I can show the cursor. You see here this maximum water holding capacity is around, correct. So maximum water holding capacity. So maximum water holding capacity is this this one, correct. VD 369 highest value. So the other soil type showed moderate to lower capacity while lowest rank was given. So by basically I am considering different things like morphometry. Why I am considering the water holding capacity? Because to prioritize the basin, correct, to prioritize the basin where we can apply different approaches for controlling the soil loss. Then we have considered the Rusley, this compound factor and field capacity. We have given the weight, this weight for Rusley this weight, and for compound factor this, by using the HP actually, and then field capacity and all, and we computed that. The priority we have given, maximum priority we have given for this Rusley, and then second is the compound factor, third is the field capacity, and based upon that we have given the ranks. So Rusley is the most important thing, then second is the compound factor, and third is the field capacity. So based upon all those things, we have prioritized the maps, prioritized the area. So there were total 30 subbasins, and 30 subbasins were categorized as a very low. Very low means from where the soil loss is minimal, then low where the soil loss is slightly higher compared to that one, moderate in the top of the hills like mountainous region, very high in the western part of the basin actually, the western part of the basin. Why? Here the thing is this, like here the forest was removed and the glacier and the snow was melted, so there was a barren soil, and very high only few pixels were there. Very high, for very high there were only few pixels, so that was the thing. The outcome showed that hotspot region of soil loss in the GRB. So by looking these maps, I cannot say that all kind of measures we can apply, similar kind of measures we can apply everywhere. We need to have a region specific measures for controlling the soil loss. High prioritized zones are this much area, which is about approximately 9.30%, 30%, and the moderate zones we have around 46.72%, and low prioritized area where we does not need too much priority for arresting the soil loss. Okay, so this was the area, and then we have developed the hypsometric integral curves also for the basin. We find that there were the area we have young, mature, and monodog, old kind of old, that one, the high. Fine. So the HI value of subbasin is 0.3. It means that 30% of original rock mass still exists in that subbasin. HI value like this one, the subbasin number is this one, the subbasin number here. The rest of the subbasin, almost 50% has value between 0.3 to 0.6, while others are below. And so means, why, what is the meaning of this? What the meaning is this, like how much soil has been removed, correct, and how much soil has been removed from that basin. Okay? So this graph is telling this. So similarly, these are the total graphs actually of all 30 subbasins. Right, and some others are concave. So the graphs are convex and concave. So convex upward shape shows, convex upward shape curves are young stage, while concave, this convex upward, and then you have a concave, yeah, or a S shape, concave upward, convex and concave upward, correct, or equilibrium curves. So these kind of graphs helps us to know whether the sub-basin or the basin has potential for releasing the soil. Correct. So the hypsometric analysis outcome depicts the geomorphic age of the basin as old and mature stage for BM. So so now I have performed the study related to discharge. Second is related. Hello, 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 hello.
Thank you. A gente vai dar início, então, ao momento de perguntas.
I'm audible, no? I'm audible.
Sorry.
I am audible. My voice is clear. My voice is clear.
Yes, it is.
So I have around like 5 minutes or 10 minutes.
Ele quer saber se ele tem 5 ou 10 minutos para se ele ainda tem 5 ou 10 minutos.
Oficialmente eu termino o tempo agora, né? Já deu 50 minutos.
Mas
se quiser finalizar.
Your time is up. So if you want to finalize your presentation, this is the time to do it.
Okay. Just give me 5 to 2 minutes. Like, okay, so this this is visible actually. This slide is visible. I hope it is visible. Yeah. So quickly, actually, I am going to first. I have performed the hydrological study. Then I have performed the selection of the dam, and now I have using both the combination. Okay. So here this model actually we have developed the future rainfall pattern. Correct. Future rainfall patterns, and those future rainfall patterns we have considered in our modeling study. So the modeling study, we have considered this in the modeling study. R factors. We have developed the R factor is one of the most significant factor for basically understanding the soil erosion, driven by the water actually. The loss of topsoils through the water. For that case, we need to understand the rainfall erosivity factor. So we have developed the future rainfall erosivity factor, and those rainfall erosivity factors we have used in the Rusle models, and then we have predicted the soil losses. Correct. So the soil losses, these are the soil loss maps. So conclusion like this: the expected rainfall erosivity for 585 scenario 585 excess can ESM IPSL model was found to be high, followed by SSP 2.5 this is basically genuine region, like like if CO2 concentration is more, then you will find that high rainfall high rainfall, and if rainfall is high, then you will find that rainfall erosivity is high. So the SSP 585 scenarios of excess CAN-ESM IPSL, we saw that more soil erosion is if we are considering the excess ESM model rainfall to develop the rainfall erosivity product, then we will find that there is an increase of 35.93% in the soil loss in the basin. Correct. So overall my presentation is this, like if we are if we are going to increase the greenhouse gases in the environment, then we are going to see that after mid-century there is a sharp increase in the rainfall, and that sharp increase in the rainfall is going to enhance the rainfall erosivity, factor, and that ultimately affect your soil loss, driven by the water. Correct. So in Assam, we have continuously floods, and people are continuously protecting their agricultural field or their homes. And in future, we are going to target how the glaciers are affecting the soil losses. So these were my just brief.
Bom, então agora sim vamos dar início às perguntas. Então, a gente vai fixando aqui na tela e você vai auxiliando o palestrante na hora de respondê-las. Estava mutado.
So there are few questions.
Yes, we are going to start the questions. We are going to put in the comment sections, and I will be translating them to you, and then the answers to the public.
Yes. So first question, as I can read, Alice da Silva. She has asked, like, Himalayan region is quite mountainous and is home to several villages and small population groups that are geographically isolated on steep soils, Nepal and Pakistan. Yes, that is correct. Actually, in Nepal, Pakistan, or even in India also, we have geographically isolated regions. Correct. And but even though now governments are trying to develop the IoT that kind of networks, actually internet kind of IoT, basically, with internet operating networks, so that people can communicate during this hazard or disaster. People can communicate, and there is some facility. Actually, we have this national disaster relief teams, actually national disaster relief team, state disaster relief teams. So people send the messages through phones, or even the early warning systems are there. People, the forecastings are there, that like in this region there is a high chance of heavy rainfall, and you need to there is no need to go out in the fields. Okay, there is a early warning forecast for the, even for lightning also. But somehow the things is this, like the environment is the atmosphere is very complex, and the habitable place is very complex. Okay, so still people are developing, actually. That is the thing. Correct, that in the steep slopes, Nepal and Pakistan, even in India also, people are geographically isolated, actually. And the thing, if you read the document, then you will find that the people who are residing in the mountainous region, there is a culture to reside at the top, so that people can identify the threats which is coming from the ground. Okay, that is a cultural activity also there. So I hope, yeah.
Professor, 1 minute so I can translate to the people, so the answer is not going to be too long for them to understand.
Okay.
Praticamente ele está dizendo que, apesar da região do Himalaia, Nepal, ser uma região muito íngreme e muito profunda, o vale muito profundo, com o uso de algumas adaptações de IoT, né, no caso, Internet das Coisas, as pessoas agora não precisam ficar à mercê do clima, do tempo, para poderem relatar os fenômenos e os acontecimentos que estão ocorrendo no momento, para que as autoridades tomem as medidas cabíveis e que isso entre no rol de informações também emergenciais do que está acontecendo no solo e o que pode acontecer, o que pode vir de cima e, obviamente, rolando, né? No caso, neve, deslizamento e esses tipos de eventos. E eu vou pedir para ele continuar. Please, professor, go on.
Yeah. So second question is, do you know if there are any plans or studies? Yes, for these people to adapt in their lifestyle and perhaps relocation if the soil erodes and permanently becomes a danger to the villages. Yes, there is a government plans to relocate to rehabilitate in the area which is less prone to the erosion. And yes.
So I'm going to translate now. Ele disse que tem planos de contingências para que a erosão seja mitigada ou até tenha um fim, né, seja parada em certos locais, que são os locais mais vulneráveis, onde a população também pode ser mais afetada, não só economicamente, mas com relação ao próprio risco de vida também, porque há certos eventos que podem fazer com que as pessoas, né, a população fique à mercê aí de eventos extremos que possa afetar a saúde deles também como um todo, seja nos vilarejos mais afastados ou em vilarejos que tenham acesso também a transporte e essa infraestrutura um pouco mais moderna. So, Professor, I think Anna is going to put another question for you to answer. Ana, por favor, se tiver outra pergunta.
Tem, a próxima é a do José. José
Next
Júnior.
one from José, my advisor.
Yeah, your advisor, why did not use the dynamical downscaling technique? Actually, we were not having that time we don't have the servers actually for running the RCM models. But now we are looking for this downscaling of the CB6 model through dynamical downscaling. We are going to use it very soon.
I'm going to translate now. Thank you. Ele falou que na época do estudo não tinha como fazer o downscaling, nenhuma técnica de downscaling, porque comparando o CMIP 5 com o CMIP 6, para fazer esse tipo de aproximação, né, no caso o approach, seria muito dispendioso. Mas agora as novas pesquisas dele já estão incluindo o downscaling, as técnicas, e quando os resultados estiverem sido introduzidos e estudados e serão relatados, ele vai falar melhor sobre o downscaling dinâmico. So, Professor, I just translated that. Ana is going to put another question for you. Ana, por favor.
Aí a próxima é a minha. Aí a minha.
Yeah. Your question is, since this is your question, since agriculture is essential to life given climate events and erosion, what soil management and would you recommend? Are there natural methods like using plants and other than materials? So as I told you that as I show you my map actually, in that map you have different parts, and in different parts you can apply different techniques. Like in the steep slopes you can go for the terrace farming, and in the or agroforestry system you can do the agroforestry system, or you can improve the irrigation, like you can go for the drip irrigation kind of thing, so that the soil is not get too wet, so which can easily moved off. There are different actually approaches for different regions, and we can go for the crop cycling actually for applying different types of crops. Crop rotation things are we can consider, so that the root zone and all, that is not going to affect, and deforestation we should control the deforestation.
So I'm going to translate it for everyone. Basicamente o que ele falou é que, apesar de existir 4 regiões distintas, reflorestamento seria uma das opções mais viáveis, principalmente para os locais mais íngremes, né, com slope maior, um desnível maior, mais aprofundado, mas que também há tipos de plantações específicas para cada tipo de solo, né, mais arenoso, menos arenoso, mais seco, mais úmido, seria também essencial para manter aí a agricultura, né, que é parte essencial da vida lá para os moradores, para a região, e que também essas opções seriam viáveis para mitigar o desmatamento na região, né, que faz com que a erosão aumente e seja mais prejudicial do que benéfico. So Professor just translated that. Anna is going to put, if it has another question and time to do so. Ana ainda tem tempo para. So, okay, it is still time for another question, and Anna is going to put.
A próxima é a da Gabi.
Yeah. How can the use of remote sensing technology contribute to the early identification and prevention of accidents caused by erosion processes? Yes, actually, now you can see that we have also used the combination of combination of technology combination like drone and UAVs we have used, and the drone and UAVs we have used to identify the sensitive areas, okay, the susceptible areas. If we identify the susceptible areas, then we can go for the remedial activities. We can apply the remedial activities to prevent the accidents and reduce the chance of erosion processes. So that we can apply actually.
Okay, I'm going to translate it. Thank you again. Basicamente, ele falou que sim, o sensoriamento remoto ajuda bastante para o estudo da erosão do solo, não só com relação ao solo, à vegetação em si, mas também para ver os locais com maior vulnerabilidade, uma vez que também pode usar modelos preditivos para fazer esse acoplamento com essas informações, e também usar o SIG ou o GIS, né, que é o Sistema de Informação Geográfica, para aprimorar cada local especificamente, para não ter nenhum tipo de erro no fator, principalmente da parte de inclinação, que é uma das coisas mais importantes ali no Himalaia, né? A cadeia de montanha é extremamente alta e o sensoriamento remoto não só é bom para o tipo de estudo, erosão do solo e afins, mas é fundamental também, e eles também utilizaram e utilizam esse tipo de técnica e procedimento. Thank you, Professor. I'm going to ask Ana again if there's time and if there's another question. Ana, ainda tem alguma pergunta e ainda tem tempo?
Não,
Gente?
não temos mais perguntas.
Okay,
Agradece,
Professor.
por favor.
Yeah.
No more questions. If you please be kind to finalize your presentation, tell more about your update on your researches about the Himalaya and anything related to. Please, if you be so kind, go on.
Yeah. So actually, you know that the erosion, and similarly we are also focusing on the contribution of glacial belt, like how much glacial belt is coming in the water actually. So if many studies, like people have performed many studies by considering that the the atmospheric event, like atmospheric or ocean events. Atmospheric and ocean events means atmospheric and ocean, like ENSO, or in India we have Indian Ocean Dipole, El Nino Southern Oscillation, or Pacific Oscillation. Okay, so these oscillations, these extremes can control the hydrological extremes, or these extremes impact the hydrological extremes. If these impact the hydrological extremes, or we can somehow develop the tele connection between these the atmospheric and ocean extremes and to our hydrological extremes, then we can go for the for better understanding, like for better understanding in terms of how much glacier is going to melt and how much it is the melt water will come to the our river system, so that our reservoirs, or how much this water is taking or transporting the sediment load to the reservoirs. And the reservoirs sustainability is a big challenge, is also a big challenge under the changing climate. If sediment load is very high, then you will find that the reservoir is going to be cannot sustain, actually cannot sustain more water, because so dredging kind of things. And we are also focusing on running high resolution high we are basically focusing on WRF weather forecast, weather research forecast model for forecasting our these rainfall scenarios, and then those rainfall scenarios we are going to consider in our hydrological modeling. So these kind of works we are doing for the Himalayan region, and we are also focusing on multi-cryospheric hazards. Multi-cryospheric hazards, like if there is a cloud burst, then after cloud burst there is a chance of glacial lake outburst in the Himalayan region, and that glacial lake outburst is going to form the flash floods in the lower region. So that is very common actually. Nowadays it is very common in the Himalayan that is cloudburst and glacial lake outburst, and many regions in our country, and even in Nepal also. You will find that due to rise in temperature, there is a glacial melt, and that lake is formed, and then the lake is going to be disrupted. Okay, so that kind of things we are trying to model, and we are trying to give the suggestions to our governments and our committees actually.
Thank you, Professor. I'm going to translate. Eu pedi para ele fazer uma atualização de como estão as pesquisas deles e qual o foco principal, o que ele pretende fazer e qual o rumo que as pesquisas dele estão no momento. Ele disse que, basicamente, para resumir, rodando modelos preditivos para ver como é que o degelo, né, das regiões mais altas, as regiões de glaciais, vão influenciar a bacia hidrográfica na região lá da Índia e do Nepal, né? Como é que vai afetar também a erosão do solo e a sedimentação também desses rios e dessas regiões. Basicamente foi isso que ele falou, muita parte técnica, principalmente com relação à modelagem, que é, acho que eu diria, como ele mesmo falou, um dos pontos mais importantes, fazer com que o modelo acoplado tenha todas as informações para que a rodada seja completa, completa no sentido de ter todas as parametrizações, toda a parte microfísica, toda a parte de uso e ocupação do solo, sedimentação também, acúmulo de sedimentação, drenagem, para onde vai descer mais água, por onde vai descer menos água, o nível de degelo, e isso tudo com relação à temperatura, obviamente, influenciada no mundo todo, e vai seguir a pesquisa dele daí. Ana, quer que eu faça mais alguma coisa ou já posso falar para encerrar?
Não, eu só tenho que dar uns avisos finais e depois a gente já pode encerrar. Então,
Pronto, eu posso dizer a ele que já encerrou, no caso, né?
A parte dele sim, eu só preciso realmente dar os avisos finais.
Okay, Professor Singh, we all want to thank you so much for your so much incredible presentation. I know we all know your time is very precious, and it was so great to have you here in this event. So Anna is going to end the event by saying some comments, and we are very pleased that you show up today and give your presentation. Thank you so much. And now we are going to hear from Anna, and we are going to end this lecture for the day. Thank you so much.
Yeah.
Thank you so much. E aí, só para avisar que a próxima palestra que estava agendada para 15 horas vai ter que ser cancelada, pois o palestrante Luiz Cláudio ficou sem internet, então a palestra de efeitos locais e remotos dos incêndios florestais e queimadas na qualidade do ar dos centros urbanos não vai ocorrer agora às 15 horas. E a próxima palestra vai ser, então, às 16 horas, com a Cristina Calheiros, e a gente vai ter esse pequeno intervalo e vai voltar com a palestra Experiências Educativas no Pacto Europeu para o Clima e Soluções para Minimizar os Impactos de Eventos Extremos. No mais, a gente agradece em nome do Programa de Pós-Graduação em Engenharia de Biosistemas, agradecemos ao palestrante por estar aqui com a gente e agradecemos também a todos os participantes que estiveram aqui no chat, trocando com a gente, e nos vemos na próxima palestra às 16 horas.